Hello and welcome to the Unit 10 podcast on Section 16.3. Today we're going to be discussing thermochemical equations. I'm Mr. Sakaguchi,
And I am Mr. Lin.
and let's get going here. So writing thermochemical equations, this is basically a balanced equation that also includes energy changes as expressed in enthalpy changes, known as delta H's.
So you'll know that a reaction is exothermic or endothermic by the delta H value. If the delta H value is negative, as is shown below, then you'll know that it's exothermic because energy is being released from the system. Whereas it's endothermic if the delta H value is positive because energy is going into the system, so it gains energy.
A couple of operational things. So sometimes you may see a thermochemical equation written like this where it's the reaction and then the delta H is written next to it. There are other instances where you may actually see the delta H value written in the reaction itself. So because this is exothermic, it would be this product plus this kilojoules. Whereas in the endothermic reaction, the 27 kilojoules would be on the left-hand side of the arrow, in case it comes up. We also have enthalpies of combustions, and this is basically a specific energy change for 1 mole of a substance as we burn it.
Right.
So for this reaction, the heat of combustion this is how many kilojoules would be released per mole. Okay. One other thing to keep in mind here is standard enthalpy. So whenever you see this little degree sign, that means standard conditions for thermodynamics.
Right, and what this means is that the reaction is taking place at room temperature, so 1 atmosphere, 298 Kelvin. This is different from STP conditions for gases because STP is 1 atmosphere at 273 Kelvin, or freezing point of water. So there is a difference between the two.
Yeah, so they're not the same thing.
Right.
Calculating energy released in a reaction like this. So let's say we have a problem like this, a bomb calorimeter. We're measuring how much energy we would expect if we burn 54 grams of glucose. Well, we have our heat of combustion. We have how much glucose is present in the calorimeter. And basically, we can use those two values together in order to figure out the energy release.
So the delta H of this exothermic reaction is given in the problem. It's not written in the problem itself. It's just part of the knowns. You would look this up on a chart or table. Since we were given 54 grams of glucose in this case, first thing you have to do is realize that our delta H is per mole of the substance. So we have to convert our grams of glucose to moles of glucose. And you do this by finding the molar mass, dividing the molar mass, which is 180.18 grams per mole of glucose. Solve for the number of moles. And now we can follow through on the rest of the math because we know that one mole of glucose produces 2808 kilojoules of energy. So when we do the math, crossing out the units, we get 842 kilojoules of energy being released from 54 grams of glucose.
We also find that there are energy changes associated with changes of state. So we have some different ones to account for this. We have molar enthalpy of vaporization, and this is the heat required to vaporize 1 mole of liquid. So in other words, to convert it from liquid to gas. Vaporization enthalpies tend to be positive.
Right. And then the opposite is also true. So if you can vaporize with a certain amount of energy going from liquid to gas, evaporating it, the opposite amount of energy is also required to cool it down back to the liquid. This is known as condensation. And then on the other end, when we're going from a liquid to solid, this is known as the molar enthalpy of fusion. Fusion meaning things combine. So when liquid goes to solid, energy is absorbed, and as a result, it solidifies, and that's going to also be a positive value. Whereas when you're melting things, going from solid to liquid, exact opposite's true.
And so, as we stated before, here's our value for water for vaporization and fusion. And as we said before, the delta H's are equal and opposite to each other with respect to vaporization and condensation and to fusion and solidification. So notice how the positive values for vaporization and fusion are equal and opposite with respect to condensation and solidification.
Right.
we can come up with these uh, curves to kind of show what happens during the process of changing from different states. So what you'll notice here is that we have these lines, and then we have plateaus. And so depending on what direction we're going with the curve, um, if energy is increasing, we're going in the forward direction. So that means that the temperature is increasing to the melting point. For the solid, it melts. Then the liquid will continue to increase its temperature to the boiling point, where it will vaporize, and then from there it'll continue to go up, and then it'll do the reverse if the energy is decreasing,
Right.
or temperature is decreasing. In terms of numerically what's going on, whenever you have whenever you're increasing the temperature of a substance but the state of matter isn't changing, you're going to be using the specific heat equation. So that's why you see specific heats for each of the lines here. So if this is the solid water, liquid water, and water vapor.
So it's possible to run into a problem where you're having a temperature change within the same phase, and then also a phase change, and then um, another change in temperature within the second phase. So what you would wind up doing is you would do the calculation of Q equals C m delta T for this beginning part for the slope, for the temperature change, and then when you hit the phase change, you would do a separate calculation for how much energy goes into the phase change, and then later on, if the question asks for it, an additional calculation for the change in temperature within that phase, within this new phase, and you would add up all the energies of all three.
Now, the heats of fusion and vaporization represent the energy necessary to transition from one state of matter to another one. Also notice that these delta H's are in kilojoules and these specific heats are in joules, so you have to make sure that the units match up before you add the energies together.
Also notice that the constants also have for the temperature change, it's done in grams, whereas during the phase change, it's done in moles.
Right.
So be sure to be mindful of the units and convert accordingly.
So let's say we were going to do a change of state heat calculation. So let's say we had 25 grams of solid methanol at its melting point, and we want to know how much heat it takes to melt it. So because it's at its melting point already, we don't have to use the specific heat equation. We can simply use the heat of fusion. So first thing we would do is we would find the heat of fusion for ethanol, which happens to be 4.94 kilojoules per mole. And then since this is in moles, we have to make sure our methanol is in moles, which it isn't. So we're going to have to convert and find the molar mass of methanol.
And we already know how to do that from stoichiometry.
And once you have that, then you can multiply the heat of fusion by the moles of methanol. And this is summarized in this equation here, where we start off with grams. It's 1 mole over 32 grams. 32 grams is the molar mass. Remember, we go to the periodic table to find how much C, H, and O weigh. The grams cancel out, so now we're in moles, and then the moles subsequently cancel out, giving us the energy necessary to melt that ethanol.
Right.
Or methanol, I should say. I'll let you do this.
All right, so here we're going to be dealing with, let's see here. We're going to be dealing with the mass calculation, like how much mass must be there if it's a certain amount of energy is being released. So since we're dealing with methane here, and we can find out what the delta H of combustion is from a chart, and it's given in this problem, so it's negative 891 kilojoules per mole. And if that's the case, all we have to do is convert from our kilojoules of energy that are produced, 12,880 kilojoules, divide by our delta H of our combustion, which is 891, to find out how many moles of methane there are. Now the question is asking for what mass. So now that we know our moles, we can convert to our mass, and you do this by adding up the elements from the periodic table and getting 16 grams, and follow through with the units canceling out, and you wind up with 231.3 grams of methane being used to release that amount of energy.
And notice how we inverted the molar heat of combustion here. So notice how it's upside down in this one, and that's necessary to cancel out the kilojoules because we want moles in this case.
What really is going on is, yes, this is negative 891, and since this is 12,880 kilojoules of energy being liberated, that means the system is negative 12,880, and this is negative 891. The negatives would cancel out. That's why the answer is in positive numbers, grams.
And that's it.